start. So today we will cover about the medical image formats, image enhancement and ROI analysis, and then straightforward moving on to the feature engineering part and building the ML models, and finally testing the models and checking its accuracy. So for the medical image formats, yesterday we dealt with the PNG images, JPG images, PNG images, but when we talk about the medical domain, there is a DICOM format which is almost used in every device if we are capturing something, maybe in eco device or in case of thermal imaging type of a thing. So there is a DICOM and then there is a Nifty. So in case of DICOM, like for the case of PNG or JPG, only we have the image data, only we have the data and we have the pixels and we have to deal with the image array. In case of DICOM, we have some additional information, like we can, if we have some DICOM file, we can see which modality it belongs to. Like suppose it belongs to the CT scan or it belongs to the ultrasound scan. And based upon that, we have many other features like we can get the pixel, we can get the what is the cine rate of frame rate or the name of the patient, ID of the patient, all that is stored in the DICOM. Because when we are capturing through the device, which converts the image into DICOM format, there is usually this user-friendly screen comes up in which we have to store the information. So that all information is stored along with the image which is captured or the video which is captured in the DICOM file. And then there is Nifty. Nifty is usually used in the cases where there is 3D or 4D type of a scans or volumes is there. So we will also be covering Nifty today, and PNG we have already covered. So let's start by importing the libraries first. So first of all, uh, for the DICOM, we have DICOM library. Okay, and for the Nifty, we have this command which we will run and then it will be installed. Okay, just a second and we are good to go then. Mm, So here I have written pip with this not sign which we used yesterday. This is a way of installing in Colab. So pip install PyDicom and nibble. This library is for the nifty ones. And here I have written quiet so that whatever the libraries and whatever the files are installed along with this particular library, we don't see any messages on the screen. So we write this quiet. Okay. And then after that, we have imported the library. We have imported and then let's explore the DICOM file. So for that, let's start with the DICOM path. And yes, before that, since we don't have any files available right now, so we can directly use the DICOM module and we can export a test example from that. So PyDICOM dot data import get test data file. Usually when you will be dealing with such images, you will be having the data. Since this is an online session and I didn't want it to create a hustle, so I'm just using this online data set available. And after that, let's start with, okay, here also I forgot to import the another library which we already installed. Right. Okay. And for reading the DICOM file, we have pydicom.dcm read, and we simply will read the path. Uh, since we have imported from this particular library, we have imported this function. So we will use that to give it to a DICOM path. And in that path, there is a name city small. So we will be using that. And here we will directly read that path. Okay. So now let's see what's inside this particular DS. DS in which we have read the file. So for elements in DS, we are using here for loop and then printing the elements. Let's see. So here we can see for this particular DICOM file, here there are many things. Apart from the imaging pixels, we have many other points which many other metadata associated with this. So at this particular 008 0060, we have this modality since it is a CT scan, so it is listed there. And then at 100010, we have the patient name, which is usually entered when we are taking the scan. Patient ID is there. So these are the elements. So when we are reading this particular DICOM file, we have this metadata also available. So now let's see how can we access that data set, access that metadata. So after this, we can write, we have the path, we have the DS. So now directly we can write print modality. Since it is written in the inverted commas, so we can write anything and then ds dot get. This is how we access what is present in that modality. So this is a CT scan modality as it was listed in the metadata also. Now in some cases, in some devices, usually there is a problem that maybe modality is not present. Maybe that is not entered, or maybe the when the image was captured, the data was captured, it was unable to identify. So in that case, for modifying this and so that we don't get this error, what we do is we can write here, after this modality, we can write none. So let's suppose I'm talking about, okay, I'll show, maybe we're talking about frame rate. Okay, I don't know it's present or not. So let's test it. So let's enter here frame rate and let's see what will it print. So it is printing a none. So it is not available. So it's like if it's present, then it will print that. And to cover that case, we can also modify this particular line so that we can write here none or not applicable. Maybe in some cases the frame rate is not applicable. So it will simply print if it's present, if it will print its value, otherwise it will print not applicable. Like in this case, if the frame rate was present, then it would have printed at its value, otherwise it is printing the none. So after that, let's explore the image size, because like yesterday also we dealt with what the size or what the resolution of the image is being exported. So let's start today also image size. And for that again, comma, ds dot rows will give one dimension, and then we can perform this like this, ds dot color. Capital image size. So I was missing the comma here. So this size and rows and column. So now let's display the DICOM image which we have imported. For that, we need the array, which is also a part of this metadata which we have seen. So for that, we use the pixel array. And after that, first of all, we can see its shape. I'm directly okay, I'll write DICOM shape. DICOM image shape. So let's see, it is of shape 128 cross 128. It means it's a grayscale. It's not RGB. And now let's view that file. So for viewing, uh, we have not imported the matplotlib here so far. So let's first import that file. Import matplotlib.py plot as plt, and then start with, first of all, we will need a figure, and we can mention its dimension, which is given by fig size equal to maybe 5,5, and then plt.im show DICOM image. And we don't have to forget writing cmap gray, otherwise it will show, but matplotlib will not be knowing that okay, this belongs to the grayscale, so it will use any other colors, or it can use any other thing. Like yesterday also we were seeing like the greenish, so that is a different type of a visualization name. So for the gray images we have to write cmap gray so that it use this map. And then we can give the title as DICOM. Let's view which file we used. So this is the city scan. Now, now you have seen that along with the DICOM image data, we are having its modality and other dimensions as well. Now let's go and check for the Nifty, and we have already imported an nibabel as nib. Now for that again we need the test image. So for that we will be using this library, import data path, and along with that, so that it is visible, there is one more library, import web. Now let's see the example file. For this particular file, we need to like give this operating system .os also, as I have imported the OS. Otherwise, it would have directly been imported. But in some cases, the like we have installed that particular library, so it gets installed in our desktop. So that's why we need import OS for accessing that particular file.
Excuse me,
Then,
ma'am.
yes,
Ma'am, can you just scroll to the cell where DICOM data has been loaded, ma'am?
okay, this one,
Yes, ma'am. To the cell, ma'am, not the output.
okay. Initially, we import from this particular library, we imported the test file, and then we from that test file we used the city scan, and then stored in DICOM path, and then read that DICOM path and stored that in DS. And for
Okay,
printing the
ma'am. Thank you so
elements
much,
present
ma'am.
in, yeah. So in case of Nifty, sometimes the data which is available, it is in the zipped format. It is of format Nifty, but it is zipped because there are many slices. As we have previously discussed, that it is either for the 3D or the 4D scans. So usually this GZ is mentioned, and this GZ indicates that the file is zipped. Okay. So now let's explore. We have imported the file, and now for the Nifty image, we have to load that. Okay, it is working correctly. Now let's explore its shape. print shape. For that, we will give the name nifty.image. This we can see the shape and we can also explore the type. Print type. So you can see it is of shape 128, 96, 94, and 2. So it what does this mean is it has 128 x dimension, 96 y dimension, 24 is the number of slices which are present, and there are two channels. Okay, for this particular Nifty. Now let's view what's there. So for that, we need the now in the previous case also when we explored this DICOM, we used this ds.array for plotting its for plotting that particular data. So now similarly for this case as well, let's start first with the data. Here we have loaded the file. Now we will extract the data from that file. So data Nifty is equal to Nifty img dot get f data. Now for plotting this or viewing this particular slices, since there are 24 slices and there are two channels, so let's start by exploring if data underscore nifty, that particular file name, and its dimension. If it's equal to 3, if it's equal to 3, then the z slice, this was x, this was y, this was z. So then z slice, z mid maybe, this is equal to data nifty. And the second dimension, because it was a 0, it was 1, and it was 2. So second dimension, maybe the mid slice we can view. So I have divided that by 2, and then that particular slice will be given by data nifty. Now since it has 3 dimensions and 2 channels are there, so I want first full dimension, second full dimension, and that for referring to the particular slice, I'm writing it like this. Okay. And also there is a case that if there are 4 dimensions, then that case we can write nifty dot n dimension is equal to 4. Then in that case, we can write so that this particular, now I'm talking about this dimension as well. So let's suppose that is t0. Let Because this can either refer the channel, or it can give the volume over time at a different time what slices are there. So let's suppose I started with this point, maybe the first data point I'm talking about, then again z mid, and these are same. But in this case, since I'm referring to that it has 4 dimensions, so here along with this I will enter t0, which I am already mentioned that it is this one. And then finally, this is elif, elif, and then finally the else loop. This is for raising the error if there is no such file present. It is usually written in this way. Maybe the dimension is unsupported. In that case, we can write unsupported dimension, and then we can have data nifty dot n dimension. So here, first of all, we get the data, and then if the dimensions were 3, we selected one of the slide. We can select any slide since the number is 24, we can select any slide. And then if the dimension is 4, we have to set one more variable, and after that we can see that. Now let's see if it's working. No, it's creating an error. At which point traceback array used as indices must be of integer type. Okay. I2, let's check this dimension is equal to 3. Yes. Anybody has to say anything? Okay, now let's display this image. Again, copying from above. We have to plot this slice image. The map gray. Here it is nifty. So this is the nifty image which we plotted. Now moving on to our next segment, that is image enhancement and ROI operations. Yesterday, we have discussed about the thresholding and how the binary and how the mask is created. Now today, we will just, it will help us to revise also that what we performed yesterday. And now let's start with image, import, data, color, filters, measure, and give it CV2. These are the libraries. Now let's start with the data. Let's suppose the data is data.coins. Let's view this data first. plt.im show image1, comma, tmap is equal to gray. So this is a gray data of coins. And now let's apply the thresholding. So yesterday we have set the value of threshold to 0.5, and the values which were values of the pixels which were below that, they were made 0, and then the values above that particular threshold value which we selected above that were made black. So now today we will be talking about the automatic threshold system, which is a very famous thresholding technique given by the OTSO, and it is also known as a OTSO thresholding. So for that, let's apply let's first of all compute the threshold value. Threshold value, it is from filters, we get this threshold also, and we have to apply that on the image. We can either have the fixed value, or this particular threshold is, it is basically it is very good in like differentiated between the foreground and the background of the image, and it is based upon maximizing the distance, whichever, like in this algorithm in the backend, various thresholds are computed, and for that based upon that the threshold value is selected, which maximizes the difference between the variance of the pixels, and then based upon that the foreground and the background is maximally shown. Okay, so let's see what value it has computed. So it has computed 107. Now let's apply. Now let's create the mask, and now how mask will be created for the image values, which are simply the Boolean expression. For the image values which are greater than this, the mask will be created, and for that particular value, the mask will be 1. We can also view the mask. I'll just print, first of all, the shape of the mask. So now for viewing the mask, as since it is a big matrix, so how can we view? We can, let's take only first 5 elements from the board. So you can see the values were true. So that's why that mask is. Otherwise, we can also view this particular mask. We will be doing that in further steps. And now we have this mask, and now let's view. And for viewing that, again copy this. This time I will be using the subplot. First of all, the figure size, let's increase that size. And then plt dot subplot 1, 2, 1. Which one? Map is gray. This is the original one. Let's write for the another subplot, which will be 1, 2, 2. Here it is mask. Again the gray visualization we need. And now this will be a binary mask because here we have applied this binary operation. So the mask will either give the true value or the false value. So it is a binary mask, and now let's view. You can see this has gray values as well, and this has only two values, either black or white. So this was the mask which was computed based upon the Otsu thresholding. Now, based on this mask, we have to segment the image. Like when this mask is there, this image is there, and then we have to apply this mask on the image. So how we do this? We create a segment image, which is given by simply the multiplication of image with the mask. Now you see here, it will have multiple values between 0 to 255, and it has only 0 and 1 values. So for, let's say, extracting these particular coins, which are marked with the white color, so we apply this binary mask on this image. So for that, we simply multiply these two, because this is a matrix of 0, 1, and this has some values. So where there will be zeros, that particular element will be removed. So again, let's view. And this time, let's take 3 subplots. First will be second, and now for the third one, let's have this segmented image and name it as segmented. So you can see when this was multiplied with this, we get this segmented mask. Now in this case, we have extracted the mask, and now we can extract the mean intensity in the ROI, region of interest region. So for that, let's say ROI metric is given by the image 1, which was the original image, and on that the mask is applied. So that particular ROI is applied on the mask only, like when the mask is overlapped with the original image in that case. And now let's compute its mean. This is how we calculate mean intensity ROI metrics. And for the mean, we can simply use mean. And then we can print this. Print number of ROI pixels. We can also, like here you can see it is a very big number, so we can also round it off so that we can see round this maybe up to 2 places. So it is this. Okay. So this is the overview of so far the image processing part, in which we have applied the OTSU thresholding and also viewed about the DICOM and the Nifty image formats. Now let's delve into the machine learning part. If you have any queries, you can let me know so far. I think everything is clear. Don't forget to write subplot, and there are 3 dimensions, like we are talking about one figure, 1, 3, like one space is divided into 3 parts. One space is divided into 3 parts. And then for referring to the first plot, it is 1 or 2 and 3. Yesterday, when we were using the 2, 2, maybe here we were using 2, 2, and in that case, we were also using that AX0, AX1. So for that, the correct measure was I provided the corrected code only. So for in that case, we have to, like, for plotting an image at particular number. Let's suppose I'm talking about 2, 2, 1. So for that, suppose this is the way that how we plot that image in particular subsection which we have created. So any doubt? I'll just take a break of 1 minute and then we can move on. You let me know if you have any queries. Just scrolling here. In this case, the image was so already grayscale. Otherwise, when we are dealing with the image processing operations, it's better to convert them into the grayscale. Now, this was the Nifty. There were many slices as it was printed here. We can also, rather than by here, what we are doing is we are extracting this particular element by this, and then we are dividing by 2. Remember, we are dividing by 2. Let's suppose I'm directly giving here 20, maybe some number 20. So it will get printed because this is also a number only. It's just an operation to get that number. Otherwise, we can simply write that number if you know that what slice you want to work with. So after that, this was the image enhancement operations. Thresholding, O2 threshold was applied. And then the mask, we obtained mask simply by applying the Boolean expression. And then the mask here can be seen that it only contains a 0 and black, 0 and 1. And then finally this. Now let's start with the machine learning part. So in machine learning, the steps, basic step, which is, first of all, we need to have the data. We need to have the data, and then we perform after the data. What we do is we need to explore the data so that we know that what data we are dealing with, if there are any missing values. So we usually, in the case of numbers, when we are dealing with the numbers, so if there are any missing values, so we have to append that, or if there are some values which are infinity, we have to deal with that. So that is a part of a pandas library we use for that basically. But in the image cases, there are no such complications. But when we are talking about maybe regression, where we have to deal with the numbers, at what number will be predicted next, maybe in that case we have data exploration is a very important stage. And after that, first we have the data, then we explore the data, and then we apply the pre-processing, we extract the features, and then finally we apply the model. So this is a basic pipeline of the machine learning. So let's start with importing the libraries. So
क्या क्या बोले पापा थोड़ी सर आए
आने वाले होंगे सर, लेक्चर होंगे.
okay, let's start. So we have this import first library, and although I have imported them above, but again I'm just writing it so that you memorize them. And then from image import data, color, and filters. So far we have not used the color, but we have used the filter. Yesterday we used the Gaussian filter, and today we use the auto thresholding, which is also present in the filter. And then next, import tv2. And now the main library. Since we are using this sklearn, this is a basic which helps us to build the model. So here we have sklearn.model selection. From that model selection, we have this train, test, and split function. Okay, so again from sklearn, there is matrices, and we can import accuracy. Usually we need the accuracy, but if there is a multi-class problem, then we need other matrices as well. Fusion matrix, and okay. And now let's import the models. From sklearn.svm, we will import SPC. From sklearn.linear model, we will import logistic regression. From sklearn.ensemble, import random forest classifier. And finally, this seaborn. This will help in viewing the confusion matrix later on. So let's import these libraries first. So now let's start with the image, with the data set, because we have to perform the machine learning task. So we need the image, not just images, we need a data set proper. So let's explore what is there in this image import data. We have seen this yesterday as well. Print CSIR. So we have astronaut, binary blobs, brain, and so on. This data was present. Now before that, let's start with data and just view that all these data have same shape or not. The coins which we earlier used, let's see its shape. So it is a grayscale image. Now let's see data dot astronaut. So this is the RGB image. And also one more thing that we have to take care is we need same size of images. But anyhow, we are just starting. So let's see. If we are selecting, suppose this astronaut, we need grayscale images because we want every image to be of same pattern, right? Like either use all the RGB or use all the grayscale. So let's start by creating a data set first. So let's suppose I'm taking the first image of points and then next image of data dot summarize. There is a very basic image processing image. And now next, as we have seen that astronaut shape is there, it is RGB. So we will be converting that to RGB to gray. I'm talking about this image and this curly pieces. Okay, so let's suppose this belongs to class 0, class 1, and class 2. Okay, and now let's club them so that we get a one particular file. So let's club them by simply image 1, image 2, image 3. We have concatenated this, and let's suppose the labels are, as we have already mentioned, 0, 1, and 2. Okay. So now let's view these three images. Now we will use another advanced coding technique to view this. Not advanced, just a level up, so that we don't have to plot each and every, and we have to like extract image 1, image 2, and image 3. So for that we will use loop img in, remember, enumerate, where we give the numbers. Enumerate, what we want to enumerate is images. Then we will close with the semicolon, and then let's start with subplot. So 1, usually we write here, since there are 3 images, so 1 comma 3. And now what I will do is, as I am extracting the index, so let's increment that in every loop. plt dot im show the image, and the CMAP is gray. plt dot title. Here I'm using this time the f string. Okay, this is also used in with the print command. So here I want the class, and for the label, because I want the label to be printed along with that, label, the name is labels, and now plt dot access. So in this one particular go, I am able to print all these 3 set of images, and we have the labels which say class 0, class 1, and class 2. Look, I don't have to write the title each and every time. It is simply the thing which is present in the inverted commas, and when we apply this round curly bracket, whatever we write that inside, it is a name of the variable which we have already written. And then for indexing that variable, we are using this scare bracket with I we have already computed here. So this small set of code has plotted these 3 images instantly. Okay, now we are using these 3 images. Now we cannot work with these 3 images and make a ML model work. Okay, so for that we need a huge data set, or not just huge, we just need a good amount of data set. So for that, let's create the data set by repeating the images. So this is what I was talking about. This is a part of data exploration. Like we have to understand the data. So for that, as you have seen that we have different types, different shapes were there. Data dot coins, and let's quickly see what was the shape of camera which we are using. So you can see the data dot this camera, it has 512 512. Astronaut is, it was grayscale. it has been converted to grayscale and it has some another dimension. So for dealing with this data set, what we need is, first of all, we have to resize the data set. And for resizing, let's start with, again, let's make a function. Let's suppose its name is resize image, because I want that resizing to be performed at one go. Otherwise, I can simply apply this resize, whatever the function is there, to one by one the images. But to harness the power of the functions in the Python, let's quickly make a function which can do that for us. So what we want is, we want to pass the image and we want to pass that what size we require. Let's suppose we require 64,64. So for the function definition, we ended by again colon and now perform the operation. CV2, from the CV2, we use the resize, and for that we use RMG, the image to which size we want, and then there is interpolation technique which we can use, which is simply, let's suppose, take this is just a name of interpolation technique, and then image equal to image dot. I'll just explain this in a minute, that what's happening here. Float 32. Finally return the image. Okay. So here, let's see what was the data type. What was the type of this image? Okay. So for that, we can write data dot astronaut type. So you can see this image particular belongs to this format uint8. Okay. So here what I'm doing is, when I'm performing this, and we have to convert it, we have to divide it by 255 for normalizing. So in that case, when I will divide that particular image by 255, it will be converted to float. So for that, I'm writing that image to float, and then it will be divided, and then it will return the image. Now let's apply that to all the images. Let's say resized. Now we will use the list comprehension technique. We will call the function resize image, and inside that we will simply pass im, because here we have fixed the variable. We don't need to mention that. For im in dataset was images. Okay, we have to run this first, and now this. So now all the images will be resized. We can check that images resized. Let's take the first image and now see the shape. You can see now that image has been converted to the shape of 64,64. So since the data set was of different size, we we resized that whole data set to this particular 64,64. Now since we have to create a data set by repeating the images, now let's perform the data augmentation. So for data augmentation, let's start with importing a number, file this random. Now let's define the augment function. Augment, what we have to augment, the image. We can name it, and we can write anything inside this. Image one. Okay, so first of all, before we start with the data augmentation, just don't forget to create a copy of that original image, otherwise it will be altered. Okay, so image dot copy. Okay, this will create a copy of that particular image which will be called, and then let's apply this loop. If now this will generate some random number, and if that number comes out to be maybe suppose less than 0.5, then I want this condition to be implemented, that it will update this argument with np of random. This is for adding with the noise. I want this the standard deviation. Okay. So this is for adding the noise. Now let's suppose we have to flip the image as well. Again, let's set a number random.random, and if this number is, let's suppose, less than 0.4, so what we'll do is augmentation will be np dot, it is for flipping. Yesterday we simply used that 0 and 1 number, it has a keyword also, so we will be using this today. Flip lr, it is used for horizontal flipping. And now again, once you know the logic, then you can go with using these keywords. Otherwise, if you are starting, then you have to understand that what keyword is actually doing. So flip. Now I'm using, this is for horizontal, and now this for vertical. Here I'm writing flip UT augmented. We have to take care of the spaces. Yeah, so this one was for adding noise, this for horizontal flipping, this for vertical, and now let's rotate also. If again this number is, let's say, suppose less than 0.6, so how to rotate this particular image? We can make a number. Okay, for that we have the library, the function np.rotate 90. It will rotate by 90 degree. And now here we can fix that how many rotations it want. Like if it that's to be rotated one time 90, two times 90 it means 180, three times 90 means 270. So for that, let's give a controlling number which will be computed. At every iteration, it can vary between 1, 2, and 3. And after that, it will be given inside that another function. Now let's also add some brightness to the image, and for that, let's again use the function np dot random dot uniform, and I want these to lie between 0.1 to 1. It will create a number, and then finally it will be added to this. And after all these operations, what we want is we want to check that it doesn't exceed our range of 0 to 1. np dot clip. Since we have normalized, in this case, since we have normalized it, so now every value will be either, initially it was varying up to 0 to 255. But as we are dealing with machine learning, it's better to convert them into 0 to 1 range, because 255 or otherwise these numbers, they take up space. So it's better to get every image in 0 to 1. The image will not change, only the values will be normalized. Okay, so for finally checking that this particular image lies between the range of 0 to 1, as we have already performed the normalization. Now return augmented image. So this is our small function for data augmentation. And now quickly run that. Okay, it's giving error. I forgot to put this. So it has been executed. Now let's start with, let's say I have a X and Y. X is my empty list, again Y is my empty list. And now I have to uh, apart from like we have three images initially, so I have to increase the data set. So first of all I resized them, and then I have to perform certain operations on these images and then combine them into this vector, this list vector X. Okay, so for that I am again going to write a function idx image in rate. We have used this image resized. So all the images which are present inside this, and now let's say let's take a range. So it will run up to 0 to 79. So here I'm writing 80 because I want 80 copies to be made of each image. So that total data set size reaches 240. Okay, I'll just mention here 80 for number of samples per image we require. We can change this number. Okay. So now we have to apply the operation. Now X, since this is a list, X is a list, and we have, like when we are entering this loop, first of all, we will get the first image and its index number, and then we are running a loop that says, let's suppose I ranges from 80. So for that, we want X to be appended, which is a list operation we discussed yesterday. We want this to be appended with our function name is augment and this. Again, let's make it small, otherwise it will be confusing. I dot append simply the name, because there were initially three numbers, 3012 labels were there. So we simply want that X to be augmented and then simply append that particular augmented image along with the label, which will belong to 0, 1 or 2, not 80, because basic images are three only. So there are three classes in this sample which we are creating. Okay. So after that, see in this one click, we are able to replicate all the data. Now let's quickly see. Okay, first of all, convert that to the array. Here we need the data type as NP float. Otherwise, it was NP. If you will check when you will be going through this notebook, you will check that so far the X. Okay, I'll just show it. X dot dot data type. Type of X. Okay, this was list. Wait, I'll just skip this step. I'll explain it later. So here what I'm doing is I'm converting this NP array into type of float. Now let's see. Okay. So you can see the images which we curated using the augmentation, they were of type 64. So here what I'm doing is I'm converting it to an array so that it is of type float 32. It's better because some models work better with float 32. Like further in later sections, we will be using SVM or the logistics. So for that case, they work well with 32. Otherwise, they will throw an error. So we are converting it here as 32. Now moving on to converting the array. Since it was a list, so we are converting that to array. Okay. Here we declared it as a list. Then we appended the images, augmented images, we appended the labels, and then finally the data type. Oh, sorry. Finally we converted them into array. Okay. Now let's quickly see what is the shape of our data set which we have created. Shape x dot shape. So you can see 64, 64 images. They were the size of the images, and now we have replicated them to 240. Okay. Now simply again we can see what values are stored in y. So see, there is first type of image, then there is second type, and then there is third type. Okay. Also, we can view the augmented images. Import. It's been imported. Now I will be using this, which created an error yesterday. Subplots 1, comma, let's suppose 5 images, and fixed size equal to 12, 3. Now for I in range, let's see 5 images. This was the thing I was talking yesterday. So let's see first image, and don't forget to write the CMAP gray. After that, let me show. I am just skipping it so that we can see what it generates. So you can see it has generated 5 images, and these are rotated. Augmented one we are viewing. So this was maybe the original image, and then this again it is rotated to some maybe rotated by 90, and some are brightened or some are brightened or other operation is performed. Okay. Now for viewing it properly, let's see. Now this is the actual image. If we don't mention CMAP gray, it will be a CMAP. It will contains the value from 0 to 255, but its visualization tool which Matplotlib is using is not accurate. Okay. So you don't have to forget writing CMAP gray. Okay. So far we have resized and flattened. No, we have resized the image, we have created the data set. Now what we want to do is, now in case of the deep learning, we fed the model with 2D images. In case of ML, machine learning, we fed the feature vectors. So for that case, we need that since we are having 240, 64, 64, 240 images of size 64, 64. Now we have to flatten that. Okay, so that we can fit that into our model. So for that, again, simply we can use maybe this x comma flat, and there is a command reshape length of x, and this is how we write it. And now let's view the shape x flat dot shape. So initially it was 240, 64, 64. Now that 64, 64, that particular image of 64, 64 pixels is being simply converted to a Bundy shape. Okay, so now there are 240 images with size 4096. Okay, so I think let's take a short break of 15 minutes and then start with the feature engineering and the train testing and other part. Okay, if you have any doubt, let me know. Otherwise, we'll take a break. I'll just quickly give you a recap. Imaging formats were discussed. We tested them using the data file, which is already present. And then we see that how to get that particular metadata. For plotting that DICOM or for working with the array, we extract that pixel array and then we plotted that. And then in case of Nifty, remember it is of either 3D or 2D, 3D or 4D size. So we need to see if there are 3 dimensions, if there are 4 dimensions, the fourth one can be volume or it can be the time at which that particular slice is being captured. And then we plotted that. And for the image enhancement, we simply took a image and then applied the threshold. We viewed that binary mask and then we segmented. Segmented is like we simply multiplied the original with the binary mask. And then finally we viewed the mean intensity of the ROI pixels. Moving on to the machine learning, first of all, we imported these libraries. Uh, Although this is sklearn, but it has different modules like model selection. From the model selection, we imported train test split. From the matrices, we imported this. From SVM, we use this. From sklearn again, we use the linear model. From the ensemble, we use the forest classifier. And then we viewed the data. It was of different resolution. And also its data type was uint8. So first of all, we combine them into a single variable, and then we'll view the image with this program, which was labeling all the images automatically. Not automatically, but we have automated the process. And then we created the data set by repeating the images. For that, since we are repeating the images, so for that initially we want a image set of same size. So we resized the images to 64,64. Here it was converted to float 32. Okay, now we performed this in one go. We applied this function to all the images, all the 3 images, and this using this list comprehension technique. And then for proceeding with the pre-processing, we created a augmented function. Here in the augmented function, this number will generate any number at every iteration, maybe less than 0.5. If it's less than 0.5, it will alter that image. Otherwise, it will not alter that image. So using this particular type of operations, we will ensure that all the images will not be going through same operations. Like if I'm talking about the coin image, so I don't want, maybe it's not up to me, maybe the number which it will generate based upon that, maybe it will only be added with noise and not other operations will be performed. And similarly for all the other images as well. So this was to ensure that they don't go through same steps. Otherwise, the same type of data will be created. So and then finally, for applying that particular augmentation technique on the data, we again use this enumerate function. And in here, when you are entered with this, we selected the range because we need the number 80, each type of images to reach the count of 80. Then we appended. And now you can see here the data type has been changed to float. Okay. So here since it is a float and X is basically a list, so we converted that to the NP array. And then we check the shape of this, check the Y, and then finally we plotted them. And also in the last step of the pre-processing before moving on to the feature engineering, we converted it into a flat shape, which is very important. You don't have to forget when we are dealing with ML, you have to reshape them. We have to flatten that. The count will remain same, but the 64,64 when multiplied, it will give you 4096. So this is converted to 1D rather than 2D. Okay. So let's take a break of 15 minutes and then meet back at 3:30. Hello everyone, let's start. Is my screen visible? Hello?
Yes,
Yes.
yes.
Oh, okay, thank you so much. Okay, so far we have pre-processed the data, we have performed the data augmentation, and now finally we are moving on to the next stage, that is feature engineering. So let's start with just extracting the simple basic features which we have used yesterday as well, the Sobel edges. Extract Sobel edges, in which we will use the Sobel filters to to extract the edges and then convert them into a feature vector. So let's start with feature edges equal to np array here filters dot Sobel. We will apply them on the image, and then again using the data comprehension, list comprehension for image in X. See, we are applying them on the images. So image vector is in X. We have flattened the shape, but we are applying this vectors on the images. So I'm writing here X. Okay. Now let's print what we get. We have extracted the edges. So 64, 64, the filter was simply applied. And now again, this shape, we have to fit that to the ML vector. So we have to flatten that. So for flattening that, let's create a variable. Just reshape length of edges -1 edges underscore flat shape. It's taking time. In the meantime, we can go with the another part, that is the histogram features. Hist features is equal to np dot array np dot histogram img on the images. Now in the histogram there are bins. So let's take 32 bins. We have to convert the values in the range from 0 to 1. And this is how we take its first element for image in X. We have to use the scare bracket. And now let's again see what is the size of this feature vector created using the histogram. Okay. Dot histogram image bin image 01. Okay. So here we have used the bins 32. So now 240 images, out of those 240 images, using the hist features, we have obtained 32 features. Now we have to combine all these features. For the time being, we are only using two, but there are many features that you can work with. So let's start by combining these features. Features is equal to, now we will be stacking the features. We will use H stack. What we need is, we need that original image 64, which was flattened, and then the edges which we obtained using the Sobel filter, and then there are list features. Okay, now this all will be stacked in one, and now let's view what's the final shape. Final vector shape, it is x features dot shape. So you can see initially there was 4096, and then again 4096 from the Sobel, and then from the HIST there are 32. So total there are now 8224 features. And let's not forget about the shape of Y. So it is simply 240 because there is only one element, either 0, 1 or 2. Only the same type of one column is only there. So now let's move on to the train, test and split. We have the feature vector. Now we have to train the data. And for that, let's use the function train, test and split. It will be applied on the X features, and we will give the labels. And the let's say the test size we need is 0.25, means 25% of the test data, and rest data will be used as the training set. And now this function will give us four variables in which it will divide the data into X train, X test, Y train, and Y test. Okay, so now let's quickly run this and explore the shape of X train. X train dot shape, because we have to see how many elements. Now you can see that out of, okay, the shape is same. Let's view some of the element. X train, two elements. Suppose this. Since this is the shape of the actual data, so in the training set, let's suppose these are the starting elements. Now let's start with training the models. So this is how we have split it, the test and the train and the test set. X data and the Y labels are splitted, and the train data is splitted. Now let's use these models for the logistic regression. This is just a model, logistic regression with some iterations. It has max iterations maybe 200. And once we have the model, we have to fit that model. And we will fit that model on the train data and on the train labels which are selected. And for the prediction part, we will use this log the model, and we use this predict function, and we have to predict that on the test data. Okay, and let's write that for the SVM as well. So it is ran successfully. Now for the SVM model, we have SVC kernel as RBF, radial basis function is there, which is used as the kernel. Apart from it, there are various other kernels as well. There is poly, there is sigmoid. You can use them and explore that how it is giving the different results. So again, we have to fit the model, and for fitting the model, don't forget to write X train. We don't have to use the full data. We don't have to train our model on the full data. Otherwise, there will be data leakage. And the prediction SVM model dot predict function. It will be performed on the X test. And quickly run this. And now for the random forest, RF model, let's say, and it is random forest classifier. Here it has estimators, that how many estimators or how many individual classifiers have to be clubbed, because this type lies in the ensemble classifiers. So again, we have to fit the model. RF fit on this and this, and RF predict on X test. Now let's evaluate the model. For evaluating again, let's make a function, define evaluate model. Here, what is the name of the model will be given. It will be performed on the Y test data and Y prediction. Okay. And accuracy, we have already imported that accuracy score. So based upon that, it will be computed on Y test and Y predict. And finally, let's print. Again, I'm using this F string. It gives the flexibility to incorporate the variable's name easily. Otherwise, we have to write comma, and I usually have the habit of missing that comma. And then here I'm writing that accuracy, whatever it comes, you have to convert that into the percentage. Now closing this string. Okay, now let's evaluate the model on the first model, logistic regression by test, comma, log. And now on the SVM, and finally on the random forest. So you can see it is giving us 100% accuracy. Okay, no problem. Our, we have trained very good model, it means. Now moving on to the confusion matrix. Let's quickly plot the confusion matrix. ELT dot figure big size. For the confusion matrix CM, I'm using confusion matrix. Why? It was already imported SVM by test on maybe the SVM predictions. Okay. Now using the SNS library, we are using it for plotting the heat map. And here I'm writing annotate true because I want to see the values. FMT and the CMAP. Here the CMAP is blue because it is a confusion matrix. Now just give the title and we are good to go. Confusion matrix. Yes, we have to give the label as well. For the X label, on the X side, it will show the predicted. On the Y label, it will show the actual, and finally the PLT show. Okay. This blues. So here you can see on there is a predicted side and other one is the actual. Okay, I have written the wrong spelling here. Okay, the actual, since the accuracy is 100%. So all the classes 0, 1 and 2, they were like this middle section represents that this particular class belongs to this particular label. First label belongs to this first, and second, since it's written here and here, so all the cases are true. They have given true predictions everywhere. Now let's test it on a new image. Since we don't have the image, so let's use the images which we initially had, and let's directly use that on it. Uh, Let me just write this as test image. Now we have to make sure. Now the thing is, when we are testing it on a new image, suppose we have trained the model, we have to follow all those steps that which we used for training. Like we have resized the image, we have converted, we have used the grayscale image. So we have to perform all that. So here, if I am taking the test image, first of all, I have to check that if its dimension is 3, then I have to convert its dimension to CV2, this particular library, test image, comma, CV2 dot color, RGB, gray. Okay. And next we have to resize that as well. So for that, we will use again the resize. Now I have to like change that particular image. So want the results to be stored in that particular, it has to be like overlap because I'm working on that particular image. I don't need the original test image. So I am just replacing the variables with the processed forms. So I have resized that to the 64, 64. And now quickly compute the edges, the histogram, and we have to concatenate as well. And let's see what are the predictions. So according to that, SVM has predicted 2. Logistic prediction says it's a 0 label, and RFA says it's a 1. But actually, what we have used is we have used the image which is at first place, image IM0. So let's quickly see. It was of coin. So SVM has correctly predicted that. Oh no, sorry, not SVM. Logistic has correctly predicted that. Okay, now moving on to the next important concept, that is the cross validation. So far, what we are doing is we are having a X vector, feature vector, and we are giving that to the train test split, and it is splitting up according to the ratio, which we have mentioned here, like here it was given as 0.25. So in case of cross validation, what we do is we want we don't give the data like usually the cross validation is used when we have a small data set. So in that data set we cannot give the data at once and then there is no scope of improvement. So if you want, if so this particular method is used when we have small data set and we have to avoid the overfitting. So let's see how it goes. So for that we have to again refer to the sklearn library. From that use model selection And here import cross validation score, comma, keyfold. And from sklearn.svm, okay, we already have that. Now we have this SVM model, which is SVC, and now let's here use the kernel linear. Initially we used RBF just for exploring. I'm just writing a new kernel here. And now for the how we define the k folds. So k folds will be defined using this particular function k fold. And in that we have to define how many splits we want. So suppose I'm giving here 5 splits. So it means the data set will be split into 5 parts, and for the training, 4 parts will be used, one will be used for testing, and so on. The repetition will be up to the 5. So this is how we write it. True. And this is a number which is used so that we get the same results every time. If we will miss this, then every time it will get a new data set and it will shuffle. We don't know what is happening inside that function, and then based upon that, we are unable to check the results. Like if we are running some process and checking some models, so it's better to write the random state and use that state every time. And now let's calculate the score. PM model. Now this has to be operated on the flat feature vector, and y are the only labels, and this is the k-fold which we have curated. And now let's check the cross validation scores. And let's calculate the accuracy. And split. Split. Okay, so CV score is this, and accuracy is again 100%. Now moving on to the next concept, which is stratified sampling. Stratified sampling is when we have imbalance in the data set. So how we use that? Since in this case, if I just check, write complete again. Let's check the shape of the data set initially. Print dataset shape. It was an X. And let's check the shape of Y. So it was this and this. And now let's apply the stratified sampling. But before that, let's see what is the original distribution of this dataset. Original distribution. It is used np dot bin count of Y. So it says that it is equally distributed, the labels. And now let's write stratified sampling. And for that, I need this. Here, what we have to do is in the feature vector, we have the feature. Here we have to give all the features, because uh, in the previous stage we were computing the features and then the data set was being divided. Now here, what we have to do is simply give all that feature as it is. The shapes are there, and then by then test size, let's say, let's keep it same. And then here is the stratify variable. If you want it to be true, then y. And again, let's quickly keep the random state as 42 or maybe 43. It's up to you. And so this is how we will use, well, since this data set has all the equal images, so it is bit of unclear. So let me create, demonstrate with an example. And in this stage, we combine both the steps. What we have to do is we have to write stratify while creating the test and the train sizes, and we have to give that to the cross validation like we have did it here. Okay, so in this case we will be combining both. And now for the example, let's create a data set. Let's just simply write np dot array. Maybe there are zeros, maybe there are 980 zeros plus 1 whose count is 20. Okay, so basically I'm creating a data set with 98% of class 0 and 2% of class 1. Okay, so without stratify, let okay, again using this. If I'm not using the stratify, let's see what will happen without stratify. Okay, so here we just have to check that how will the y test look like. Okay, initially in the previous case it was 80 80 80, so there was no change. So without stratify we have to check. So let's not write this and simply use the y because we have created this and then we will this as y1, then test size and maybe the random state we have fixed. And now print without stratify is np dot win count of the y test one. And let's quickly write it with stratify. Stratify is equal to true. Bin count. Okay. So we have test by one test. We have expected 4 but got 1. X train X test, Y train Y test. We So here what we are doing is we are not writing stratify Y and here we are writing. So you can see here the test of the Y1. Again there is an error, but anyways you can see here it is 195,5, but in the original case what we have divided the test as 98% and 20%, but here the percentage is not same. So once we run this, we are able to get the proper case. Okay, I'll rectify the error and then I'll share this particular sheet. Now let's quickly move on to our next part of the deep learning. So far, if you have any doubt, please let me know. In case of stratified and other case. If you have any doubt, if you want, I can demonstrate the stratified case with one more example of the medical data set. But if you have understood the concept, then we can move forward with the next module. Anji, please, if you need clarification on any of the topic, please let me know. Otherwise, we will move forward. Okay, then let's move on to our next deep learning session. So this is so in case of deep learning, what we do is the steps remain the same, but like we do the feature engineering in case of the machine learning, this step is not required in particular deep learning case, because the models which we make in the deep learning, the CNN models, the RNN model, each stage of that, each layer of that model, it will extract the features itself. Like we are giving some command, we are creating a model which has convolution layers, max pooling layer, so on. So it can extract the features, low level features and high level features, and then move forward on creating that, maybe the deep learning model which can be applied onto the input. So now let's move on and start with our next module. So here also, first we have to import the libraries. Since this is a new notebook, so we have to import the libraries again. Import plot lib and now we will work with the TensorFlow as TF, and from the TensorFlow we will use TensorFlow.keras, and here we use the layers which will be used to creating the convolution neural network and the models. And again from the TensorFlow.keras, and it has some folder which is utils. From that we will import this. It is used for one hot coding. We will use that in our code. Okay, so after the libraries are imported, anyone having any doubt? Okay, using the TensorFlow import layers. Okay, we have to write now. Okay, it is successfully imported. Now let's start with our data set. From TensorFlow.keras dataset import this dataset. This is a small dataset, so it's good that we can easily explore that. Frame, white frame. This dataset is downloading. Okay, it has been downloaded. Now let's explore that what is the shape of this. After loading the data, xtrain, the variable which says xtrain, its shape is xtrain dot shape. Train, train, x test and y test. Okay, so this data set has total, as you can see here, x train is 50,000 and x test is 10,000. It means total data size of this particular data set is 60,000. So by loading this with this command, it has already like actually this data set is available online. So they have already imported them, like they have already divided the data set into 50,000 in the x train data and 10,000 in the X test data. But as we move further in this code, we will be using this X train, and then again we will split the data and use for testing. Okay, this X test is will be utilized like in the previous case when we had to like apply on the new test image. So for that case, we will use this particular data set. Okay, now let's quickly see the shape of this pie train. Since you can see the Y train, it has 50,000 and only one row is there. Okay. So for that, let's see data is like this. And here it is mentioned that the data type is uint. Okay. So now let's visualize these images. For that, let's create a class names. Since I know that these are present, so I have simply or I in range 12 dot upload. I need two rows and six columns. And again, using the shortcut trick, plt.im show, what we want to view is xtrain samples. Since we have enumerated it, so we have the index and finally plt.show. So this is the data. So actually this data has 10 types of classes, which 10 types of classes, and it has total 60,000 images. Okay. We can also write the label, but okay, no problem. Now you have to see that the data type of this particular data set is uint8. Okay. Now let's start with the pre-processing part. For the pre-processing, we have to normalize this. See, the resolution is not clear. Although the resolution is not clear for this particular data set, but when we will apply the CNN model, it will work well. But whatever data you have to like work on on getting its good resolution, at least, so that if you are working with the medical images, the doctors are able to identify and give you the ground truth of the data. Okay, so in this case, the data is available as it is. Now for moving on to pre-processing, for the pre-processing, we have to normalize it. So first of all, so for normalizing it, we will use this xtrain. We will perform xtrain And then we have to take care of the data type because we are dividing it float 32 as we did previously. And then for the X test as well, the same step. And let's print the shape. Initially, the data type was uint, and now after division, we have made sure that it is of type 32. Okay. Again, the same reason 32 works well with the models. And now moving on to the CNN part. CNN model, it has many layers like convolution layer, max pooling layer, convolution layer, max pooling layer. Sometimes there is a dense layer also, fully connected layer. So based on that, we will design our model. So let's start. Model is equal to model dot sequential. We can create many type of a model, but sequential is like we are stacking the layers one upon one. So it is the basic model when we are designing the CNN model from scratch. So in this case, let's start with first layer, which is layers dot convol 2D layer with, let's suppose, take 32 filters and the size is 3,3. And then there is activation function, which is used for adding the non-linearity in the convolution layer. Activation is equal to ReLU function, and input what we are feeding here is, let's see the input shape, train dot shape. So as you can see, 32, 32, 3. 50,000 is the total sum of the images that are present in X-train, and 32, 32, 3. It means it is an RGB, as you can see from here, and 32, 32 is the resolution size. So we will mention the input shape here. Okay, this is our first layer of the sequential model which we are building. After the convolution layer, we have the max pooling layer. Max pooling 2D. Here we will have 2 cross 2. What this max pooling does is, it after the convolution is performed, convolution layer is applied on the input image. After the max pooling of the size 2 cross 2, out of those 4 pixels, 2 cross 2 mask, it will extract the maximum pixel. It will extract the pixel with the maximum value. So this is 2 cross 2. Now again, let's build another layer, convolution 2D, and this time let's suppose take 64 filters, 3 cross 3, activation ReLU. This time we don't need the input shape. And again the max pooling. After that, let's for the last time again get this layer. And this time again 64, 3 comma 3, activation ReLU. And now finally we have whatever features we have obtained here. Like after the first layer is applied, there is some certain size. I will demonstrate how the size is computed. After the first layer, and then max pooling is applied, then second filter is second convolution layer is applied, again max pooling, again convolution filter, and like initially there were 32, then 64, then 64. So slowly the features, the slowly from the particular image, the high level features will be computed. Maybe the first layer will compute the edges, then the next layer will move on to extracting the particular shape of that particular image, which can help to identify between the different classes. And now finally, After this, we will flatten the layers. Layers dot flatten. And after that, dense layer will be applied, because once we have flattened, and then in the final layer, we want our layer to classify maybe the 10 objects, like mentioned here, the 10 objects are there. So for that 10 objects, and after this flattening, the number will be very huge. So we need an intermediate layer so that it can balance. So for that, the dense layer is there. Dense layer, let's take the size to 64. Activation, again the ReLU function. And then final, the dense layer, which will decide about the probability. Here the activation will be softmax because we have to compute the probability. It's invalid. Comma. Layers dot dense. Again, comma is missing. Okay. So now we have successfully built the model. Now let's view the model that what we have built. It will be obtained using this model.summary. So here you can see that output shape after the first convolution is this, and then moving on, finally the output is, we get a one number because there are 10 classes. So let me quickly demonstrate that how these numbers are computed. Please let me know if my screen is visible. I have shared some another screen. Please let me know if it's visible.
Your whiteboard screen is visible.
Yes, I had shared the whiteboard. Okay. So starting with initial, as you can see that we had, just a minute. Yeah. So you can see that initially the shape was like 32, 32, and it is RGB. So for that case, 3 was written. So when we fed to the first convolution layer, the formula is maybe the height of the image minus the kernel size which is applied, which in our case was 3 cross 3. Since we have not employed any padding type of a thing to the image, so this P will be 0. And we have not applied any stride because these are very basic terms which are used when building the model. And here we are taking the floor, and then we have to add 1. So at so we applied the filter was, we applied here the, it is 32, 3 comma 3. Okay, now let's see how it was computed so that the output came out to be 30. Okay, 30 comma 30 comma 32. 32 here, the third dimension represents the number of filters in which were used for computing this particular layer. And for 30 comma 30, this formula is used. So here the height, the h, maybe the y dimension of this particular image is 32, and the kernel size which we used was 3. There was no padding, so plus 0. There was no stride, so simply 1. There was a stride, but it was 1 because simply we were moving the mask from 1 pixel by 1 pixel. And
Sorry to interrupt you, ma'am.
yes,
To repeat this concept, how you can embed this formula while
okay,
training the
okay,
model.
okay. So see, this is how we have built the this model in which there are 32 filters, and the kernel size is 3 comma 3. Initial in the first layer, 32 filters, the kernel size is 3 comma 3. Okay, so as we checked the model summary, it gave us that after the first layer was applied, the output shape was 30 comma 30 comma 32. But our input shape was 32 comma 32 comma 3, 3 representing the RGB channels. So in the output shape, one thing is clear that this third dimension, because what's happening is we have the input shape with maybe the 3 slices RGB, okay? And now there are 32 filters are there. So at one time, these 32 filters will be applied, and then at first filter will be applied, we will get a feature map working on these 3 dimensions. We will get a feature map. Then again the second filter will be applied, and so on. We will get total 3 filter maps working on this RGB dimension. So for that we have this formula h minus k 2p upon s. Okay, here the stride is 1 because we are shifting the mask one by one, because we have not entered anything in the convolution feature vector now that any stride or padding has to be done. So the height, maybe the width and the height, this is of the original input shape. So 32 minus 3 plus there is no padding divided by 1 plus 1. So 32 minus 3 is 29, and by adding 1 we get 30. So this is how the initial shape came of 30 comma 30 comma 32. Okay, so now moving on to the next. In case of the max pooling, simply what we have to do is, in case of the max pooling, the shape is divided by half. The formula will be same. Since in the max pooling we are not using we are using the kernel size of 2, and there is no padding and no stride. So simply, uh, the pooling formula will be reduced to, here it was 32 minus the kernel size is 2 comma 2. As you can see, we are giving here 2 comma 2. So kernel size is 2, and divided by the stride here also. Yes, the stride here is also 2, and that's why we will get here as 15. This same formula, this same formula 32 was the initial size, and then the kernel size, and then there was no padding, stride was there. So simply 32 minus 2, it is reduced to 30. Okay, after this, and then again moving on to the next stage, after we have 15, we have achieved the 15. Now in next case, the next pooling layer has the length of 64. So again the third dimension is changed as 64, and again the same formula is applied. 15. Okay, the 15 was the original length, and then minus the size of the kernel. 15 minus 3 upon the stride is 1, pooling is 0. So based upon that, 13 is computed. Again, moving on to the next, simply this term will be halved, 13 by 6, and we have to take the floor. So that's why it will be 6. 13 by 2, it will be 6. Again, moving on to the next. So in this case, using this formula, h minus k plus 2p, I hope it's visible. It's h minus k, the filter size, plus 2p for the padding if we have to incorporate that. And the stride, usually it's 1 unless it's mentioned. And the lower floor we have to take, and then it is plus 1. So after that, we have achieved this. Now, how to calculate these parameters? These parameters represent that how many computations are being performed. Okay, so for that case, we have again the formula. For the convolution layer, the formula is, the formula is the filter size, like in our case, it was 3 cross 3, into the number of channels, which here were, you can tell me how many channels were there. Maybe we were initially working with the 3 channels. So 32 comma 3 comma 3 into 32 into the filter size, which we used was, yeah, 3 cross 3 was the kernel, filter is 32, and then simply adding this. This is k into c into f plus f. So this represents the weights, and this is the bias which will be added at every layer. So you can verify yourself that it will be computed to 896. Please check if you can verify this formula. Three cross three into the channels. There were three channels into the filter size 32 and then again 32. It will be computed to 896. And similarly, for the max pooling, there are no filters because simply we are reducing the shape. Again, for the convolution, same formula will be applied. And moving on to finally the dense layer. Dense layer, again, there is a formula. In dense layer, since we are using here the filter size of 64, 64 size is there, and before that the flatten size is 1024. So total filters it has is 64 into 124 plus 64. What I'm saying is total number of the previous layer size, and then let's say the filter size of the dense layer, and then adding it with the dense layer. So it was 1024, 1024, and then it was 64 in the dense layer, and then again added with the 64. So here, after the dense layer, the parameters were this, and then in the final layer, 10. From the previous came 64, 64 into 10, and then finally this, plus 10, 650. So this is how the model is computed and model is made. Okay, now let's move on to the compiling the model. For compiling the model, here we will use model.compile. Also, one more thing I want to demonstrate that let's see what was the y shape. I want to view what elements are present in this. Yeah, I wanted to show that there are 9, 4, 1, 1. We just viewed 4 elements of the y train, and you can see that it is of the type, it is ranging from the number between 0 to 9 or maybe 1 to 10. Okay, so these are the integer numbers. So when we are using the integer numbers while compiling the model, you have to use the sparse categorical cross entropy. I'll just demonstrate like optimizer. There is an optimizer which is used, which is ADAM, which is adaptive movement estimation. This is an optimizer. So this usually converges faster, and it is used, it works well for many data sets, and also it automatically adapts to the learning rate. So it's a good optimizer. And then we have to mention the loss. Here I was mentioning that since we have the class labels as between 0 to 9 or maybe 1 to 10, these are int numbers. So we have to use the sparse categorical cross entropy. And finally, you have to view the matrix is accuracy. Okay, so now let's quickly run that. You can see it is compiled. And now I mentioned earlier about the one hot coding. So if you want to perform the one hot coding, so for that we have to change the y train, and using this variable, I'll show you that what will happen when I am performing this. Y train to 10. Y test to categorical. Now, if I will view the shape, initially you have seen that Y train had the numbers 9, 4, 1. So now let's again see what's present inside. Y train dot shape, and now let's view the elements. maybe first 5 elements. So now you can see it is of type 0000. Just make you view first element. So see, there are these 10 numbers, and what one hot encoding does it take one class and it will treat all other classes as zero. So this is how it has for the first particular one first label. Maybe it was the number 9, as you have seen earlier also. So for that it converted that to 1, and for all other it has made 0. So after this, if one hot category this encoding is applied, so for compiling this model, you have to use, in case of sparse, you have to simply use this one. And now we will simply run this. And now let's work on training the model. Now for training, we have, let's say, the history. Let's say the history is equal to, up now we have to fit the model dot fit on the xtrain. Now remember, this was the initial data which was available as xtrain. We could have named it some another variable to avoid the confusion, but here also this data will again be divided xtrain, ytrain, and now there is a number epochs. These are hyperparameters which we set before fitting the model. So there is epochs, there is batch size. I will demonstrate what do they do, and then we have the validation split. Now from this training data set, this data set which we are feeding to the model, we are like in the ML case, we were using that particular feature vector into training and the testing data set. In deep learning, we have this advantage of using this validation split, so that every time we are working, there is some part of the training data which is like used in the validation process, so that we can check that our model is learning properly or not. So now we have given x train, y train, let's say number of epochs. Now, yes. So we remember that x train had the shape 50,000. So here, let's give the split value to 0.2, means 20% data out of this 50,000 will be used as the validation. Okay. And now batch size, let's keep batch size as 100. And let's, just for the time being, let's keep the epoch as 3. So what will be computed here is, since we have the 50,000 and we have split that into 0.2. Okay. So in the validation size, what we will be left with, after the validation, the X training data, it will be like limited to 50,000 into 0.2. So what is 50,000 into 0.2? How much number will be given in the validation and the another stage? 10,000 data. 10,000 data will be used in the validation stage, and for the training purpose, here, out of these 50,000 samples, 40,000 will be used in training. Now based on that, just a minute, I'll again tell. So I'll just write somewhere here. Okay. So out of those 40,000, as we have computed 40,000 after the data was split, now we have the batch size. Now we have the batch size of 100. So divided by 100, we will take here the upper limit. So after this, the data is like 400. Okay. Now these 400, it means at one iteration. Now I'm running this particular segment. So out of that 40,000, at this one iteration, you can see there are 400 iterations. And so there are total 3 epochs. Epochs means how many times this particular data set will be passed through the training model. So we have chosen 3. Batch size is 100. Split is 0.2. It means out of the 50,000 which we are feeding, 0.2. It means 10,000 will be used in the validation stage and 40,000 will be used in the training stage. And now how this iteration was computed? 40,000 divided by the batch size. At once this batch will be transferred. Okay, so how many batches? So how many iteration? 400. When multiplied with the epochs, we will get the total data size. Now moving on, this is training. Let's quickly write the other one so that we can view the result. PLT dot figure fig size 12,5. Now we, for this particular segment, we will be viewing that how our training went. 2,1 PLT dot plot. We save that in history dot history. What we need is accuracy, and for that we need to give the label as train. Another line we need is validation accuracy, and for that label we need validation. And title see, here we will be using them as legend as well. And now in the next, this is for the training, and now we need the loss curve as well. So for that, here we will replace that with the loss. So as this iterations will complete, we can view, okay, till it completes execution. Now quickly write the evaluate, let's evaluate that on the test data as well. So we have to compute the test loss and the test accuracy, and we have to evaluate the model on X test and the Y test. And let's print test accuracy. It's about to get complete. So it is complete. Now we will be moving on to our plotting its training curve. So you can see I have superimposed them. So as you can see here, the validation accuracy is more than the train accuracy, and here the training loss, the validation loss is less. So this signifies that there is no overfitting, because in case of overfitting, validation loss is more. Okay, so this we have done, and now let's test it on the test data. So it is giving us a test accuracy of approximately 59%. See, here I have not rounded it or not used that format percent to F, which I used earlier. So it is giving me this full value. Now let's work on making the predictions. Now predict variable in which we want to predict maybe the X test of say 10 images. From those test 10 images, okay. And now we also have these classes which we initially defined, and based on that we have this function plt its size of I in range plt dot subplot 2 comma 6 comma again using the smart trick of plotting. Test I, and we have to check the title as well. So for that, we have this variable, and from that we have this particular variable called of. Here I am writing this as well, otherwise again the scale will be visible. And finally, plt dot show. So see, the model has predicted this as cat, this as automobile, this as airplane, maybe this is ship, maybe this is a wrong prediction, this as deer, frog. So this is how we have tested our model on the predictions. Now let's visualize the filters which were used in designing the convolution whole model. Okay, so for that we have this command filter dot devices model dot layers. Let's talk about the 0th layer, the first layer dot get weight. Let's see. Okay. So in the first layer there were 32 filters and the shape was 3, 3. And it was RGB. Maybe the third one is representing that. And now let's quickly plot and see what type of filters were there. Subplot 4, this we will be viewing 4, fixed size. Again for I in range, let's say 32 F filter. We have to view the filter, so I'm taking all 3 dimensions and only working one by one on the filter count. So here, because I have automated that, so I'm just going to write this particular short mathematics trick. I am sure what we have to view is we have to view and C map is this is 1, 2, 3 I, but I am sure so you can see here, let me turn off that axis. So you can see here that these were the feature maps of the first convolution layer which were used of size 3 cross 3. This, so we have total 4 and 4 columns, 4 rows and 8 columns. So all the feature maps of the first layer are used. So see every feature, so like working with the first convolution layer, there are 32 feature maps and every layer will work on extracting maybe one feature map will work on extracting maybe the edge of right corner or the left corner. So like this, each feature map will work on some particular dimension, and for all the images, that particular dimension will then be clubbed, and then we will be feeding that to the next layer. So after that, for last part of our section, and also the time is also approaching. So let's quickly see how to visualize the feature maps. So this was the filters. These were the filters which were used, and now what output we obtained after applying these feature maps. So we will view that from the Keras models. Here we need model, TensorFlow. Okay. Here we just have to make first prediction so that it has the input layer defined. It's working. Now let's first view the first 4 layer outputs. Okay, layer output is equal to layer dot output, or the list comprehension is very useful and it can be applied at every point, either with the objects or with the variables or with the list, as the name suggests. Now moving on to the activation. Here we use model. In that, inputs equal to model dot layers 0 input. Output equal to layer. Let's see, yes, okay, it's also working. And then finally, activation model dot predict 0. Since we will be viewing only 4, so I'm changing that on a big part here for I. So you can see this was our feature vector which we obtained after applying the first feature layer or using this filter on the first maybe image, and then this was obtained. Okay, so finally this now I have wrapped up the session. I'll share the Google Colab notebooks for the today, and if you have any doubt you can ask now, or we can conclude the session for the day. Just giving a quick recap.
If any question is there,
If anybody has any doubt, you can ask me. Okay, I'll just give a quick recap then. We loaded the libraries, we loaded the dataset, we explored the dataset, and we observed that the count is like varying from 1 to 10. We visualized the sample images. We used the trick to plot multiple images using this different train lab, using this different in sorry, using this trick of I+1, and then we pre-processed, made sure that the data type is float 32, and then we built the model in which we observed that how the input shape is changed, how this number is achieved, and how these parameters are achieved. You have to remember that max pooling do not contribute to the parameter count. And similarly, if there is overfitting, in our case, there was not overfitting. But in the cases when there is overfitting, there are usually other methods like batch normalization is applied, dropout regularization is applied. So you can also explore that. And for applying them, uh, suppose batch normalization, it will be added maybe after the max pooling, and for the dropout, it will be added before these last layers. And finally, we compiled the model. We made sure that if we have not applied the one hot encoding, so we will use this frozen entropy. Why this? Because this was a multi-class classification problem. And also then we explored that how to convert the labels into one hot encoder and then applied this. Finally, we trained the data. We understood that how epochs and batch size will contribute to getting these number of iterations. And epoch means how many times the dataset will be passed through a model. And finally, we observed the training curves. Here we can see the validation accuracy is more, which is good. And here the validation loss is less, which is again good. And I am having a doubt. Maybe there was a case of overfitting. I forgot the logic. Maybe the validation accuracy. Yeah, validation accuracy when the loss is less, it means there is no overfitting. Okay. Then we performed on the test data, made the predictions and viewed. Not made the predictions. We just viewed that how the test data predictions are seen. And then finally, we visualized the filters which were used in the convolution layer 1. Here we have mentioned this 0, which represents the first layer. And then we visualize the feature maps. Feature maps are when the filters are applied to the input and what we obtain after the filter count. Maybe in the first layer, the count was 32. So we are, after the first layer, we are getting 32 feature maps. So after that, this is how we concluded our session. Thank you so much for your patience and for listening me. Thank you. If you have any doubts, you can work on these Colab notebooks and add other maybe variables, or you can explore the other data set also. Thank you so much.
Okay, so on behalf of all the candidates, all the participants, so I am thank you, Dr. Aditi, providing a wonderful session, 2 days, and she has invested so much amount of time for preparing the modules and delivering the module, and she has taken the concept from basic to the higher level, where she has started from the basic. If anybody is not aware about the Python and deep learning, so he or she might be able to do or able to reach at that level, that basic understanding or basic module can be designed in deep learning. So with these words, I just want to thank you, Dr. Aditi, for taking so much time and putting so much efforts. Thank you very much.
Thank, thank you so much, sir. Thank you, everyone.
So now we will be closing the session, and we'll get back tomorrow at 9:55. So 10 o'clock there will be a lecture of Dr. Bala Chakravarti from NIT Rourkela. Thank you. Thank you all.